Okay, welcome to my lecture. Let's talk about Young's double-slit experiment. So let me, hold on a second. Young's double-slit experiment. So what happens in a Young's double-slit experiment is that you have a slit plate. So let me actually show here a side view of a slit plate. So there are two holes. We will call them apertures, circular apertures, made in a plate which is opaque. And so we will call this slit 1, slit 2. And these are two small holes, basically, circular things. And then what happens is that you have an observation screen here. It's not straight enough. Let me try again. Oh, brother. Oh, okay, that's better. So that's a screen. And we measure the intensity on the screen. So what happens on the left side of the slit plate? On the left-hand side of the slit plate, let me choose a color here. There's a plane wave. So plane wave of light. That goes and hits the slit plate, and most of the light will be reflected or absorbed on the slit plate, but because we have made these small apertures, light will leak through these apertures. And assuming that these apertures are small, what happens is that the light coming from these two small apertures here, they can be considered two spherical waves. Okay, so that's the basic setup of the Young's double-slit experiment. So you can see that maybe a better name for this Young's double-slit experiment is Young's double aperture experiment. But it's customary to call this Young's double-slit experiment. And I have to note that once you consider these small circular apertures, and you consider two spherical waves, and this is a very good thing to do because you can deal with any shape of openings that you make here after you consider this elementary problem. Okay, so let's go ahead and describe this problem mathematically. So what you do is you measure these distances on the screen. So as an experimenter, let's say that you this is about the center of the screen that corresponds to the center of this slit to slit distance. So let's call that y equals 0. Okay, so that's this screen. We're looking on the long side of the screen, and in fact, this screen is a two-dimensional thing, but we're considering only a line, only the center line on the screen. And so this is sort of a two-dimensional problem. And so we have only the vertical axis here, which we call y-axis. So this is y, and let's say that we measure intensity here at an arbitrary point with a finite y value, or it could be 0 if it's brought here. So anyway, so that's the measurement point here. Okay, and then the light comes and hits a spherical wave, comes and hits that y point from slit 1, and another ray of light comes and hits that y point. And so these two rays of light will hit the y point, and we are seeing the effect of interference, or as a result of superposition of these two waves. So we have these two rays of light which have distances which we will write as x1. So x1 is the distance from this slit to that point, and this is x2. Okay, and this is x2. And we have other distances to consider here. So let's say that the horizontal distance from the slit plate to the screen is L. And finally, the slit to slit distance here, the slit separation, is what we will denote as D. And in a scattering experiment in physics, there is a very commonly made assumption, which is that the distance from the scattering source here, which in this case is the slit plate, to the screen, namely L, is much greater than the size of the object that scatters the light. And in this case, the size of the object that scatters light is actually D, because the other part of the slit plate doesn't do anything as far as this this scattering experiment is concerned. So the single most assumption that you need to make sure that you keep in mind is L is much greater than D. Okay, so that sets up all the coordinates that we need to remember to describe this scattering experiment mathematically. Okay, so let's go ahead and describe our experiment mathematically. So what is the thing that we measure? What we measure is intensity of the light at the position Y as a function of some t. So and we know that this intensity of any wave is actually proportional to, let me replace that equal sign to proportional to sign, because you know what are the proportionality constants are. We covered that before. And so intensity is proportional to this d y t squared. So I will call this this whole thing d as amplitude, because that is customary to do so. So it's not just a constant a we call amplitude. Sometimes we call this wave field dyt or dxt, things like that, as amplitude. So let me call this thing an amplitude. So intensity is proportional to amplitude squared. So this is the combined amplitude. So let's put a subscript t for total amplitude. So what is this total amplitude coming from? Okay. So this total amplitude is coming from the superposition of two sources of wave. So one is a spherical wave coming from slit 1, the other is another spherical wave coming from slit 2. So, but the point is that those two spherical waves are very much similar to one another. So okay, so that's ds. Let's say spherical wave ds x1t. And then the second one, ds, d sub s, x2t. So what do I mean by these two spherical waves are very similar to one another? Well, here's what I mean. One thing that I didn't quite say in this lecture so far is that these two, what's more striking than red? Maybe, I don't know, purple, magenta or so. And this light that's on the left of the slit plate must be coherent. Must be coherent. So that means the light that hits the slit 1, the light that hits slit 2, they must be basically the same light. Or sometimes they could have certain phase shift, constant phase shift. But what it means is that the light that hits here, the light that hits there, they cannot have arbitrarily changing time-dependent or space-dependent phases. If that's the case, we don't actually see the interference pattern. So here in this presentation, I will assume that the light that hits S1, the light that hits S2, they have the same phase. They come from the same light. So that's an example of a coherent light. So what that means is that the light that comes from slit 1 and the light that comes from slit 2, they are basically the same light. Okay, so these two functions are exactly the same. So that's what it means. Okay, so let's write down now the expressions for these two spherical waves. And so that function is x1 sine, let's not forget the constant amplitude A. And the reason why there is an A divided by x1 for the amplitude of this sinusoidal function is because this is a spherical wave. So the amplitude has this 1 over distance behavior. So that's why we write it as A over x1. And then sine kx1 minus omega t. And there could be some phase, constant initial phase. And ds x2t, as I just explained to you, it is exactly the same function, except that x1 is replaced by x2. So then, figuring out the interference pattern becomes a simple mathematical exercise where we just need to add these two functions, sinusoidal function divided by distance. So we'll do that on the next slide. Okay, so this is the mathematical expression that we arrived in the previous slide. But in order to evaluate this function in a more meaningful way, we must make some key physical observations. So let's remember this basic condition of scattering experiment, namely L is much greater than D. And if L is much greater than D, it's kind of obvious that x1 and x2, they are actually pretty much the same. And you can actually elaborate on this math a little bit, and that's on my that's in my lecture note online, the written version. But I'm gonna skip that mathematical step because maybe it's kind of obvious, and you can do that trigonometry or Pythagorean theorem mathematics yourself, following my lecture note. Okay, so let's make the assumption x1 and x2. And if x1 and x2 are similar, then naively one might think, well, okay, so then I can replace this x2 by x1. I can replace this x2 x1, so I get two terms which are basically the same. So I can just double this term, and then that's it. But but that's not good enough. That's actually a very crude approximation, and it's wrong. So why is that? Well, here's the reason. Even though x1 and x2 are very similar, so let's say that x1 and x2 are on the order of 1 meter or so, and they could be very similar, and their difference could be maybe a micron or maybe 10 micron. What's 10 micron relative to 1 meter? So that's 10 to the negative 6th fraction. So that's very small. However, here we are talking about an interference experiment. Interference experiment is famous for being very sensitive to very minute differences. So here's a length scale. Here's a length scale that we didn't actually talk about so far, which is the wavelength of the light. So let's say the lambda is the wavelength of the light. But if you remember, the wavelength of, for example, red light is about 700 nanometers. So visible light is 400 to 700. Let me write it better, corresponding to these colors. So let's see, purple. Where is purple here? 400 to 700 nanometers. So if you think about it, well, 100 nanometer is just a 10 to the negative 7 fraction, really minute fraction of 1 meter. So here's the deal. X1 and X2 can be different by such a minute fraction, but because this K is actually lambda over 2 pi over lambda, K equals 2 pi over lambda. When X1 and X2 are different by half the wavelength, Kx1 and Kx2 can be different by pi. Or if they're different by lambda, then these two numbers, Kx1 and Kx2, they're different by 2 pi. And phases being different by pi or 2 pi make a world of difference. That's the key of an interference experiment. So the two lengths of parameters here, x1 and x2, different by very minute number, can have a great effect in the interference experiment. So the lesson here is that, okay, so x1 and x2 are very similar. We can put them equal for these terms outside sign, but when we talk about phases, we must really pay attention to their minute differences, because that is very important in the phase sensitive experiment, which is the case here. So here's the deal. So this quantity is A over x1. I'm going to just approximate this x2 with x1, and then I'm going to factor out this A over x1, A over x1. And so what you have left is sine of, let me actually use some notation here which will simplify. So let me just use this delta, this whole thing as star 1. Okay, so that's the phase of first spherical wave. And then the second spherical wave is characterized by star 2. So that's the phase. So by star 1, I mean this whole thing, and star 2, I mean this whole thing. Okay. Okay, so what's really important is what is the difference between these two phases. Okay, so then this becomes sine star 1 plus sine star 1 plus delta. So what do I mean by delta? Delta is, so what is the difference between say this phase here, which is star 2, this phase here, which is star 1. What is the difference between the two? Well, they got the same initial phase because they come from the same plane wave here, and they got the same time because they are measured at the same time on the screen by us. The only difference is x1 and x2. So this delta, sorry, so this delta is k x2 minus x1. So that's it. This is the key quantity here. This plays the central role in this experiment. So let's discuss further on the next slide. Okay, so here's the expression that we arrived at, and let's make some important observations. So we have two sine functions here, and it's and they have a phase difference delta. So delta is k x2 minus x1. If delta is 0, or, well, 0 in angle means 2 pi times integers, then this whole this whole thing will become 2. This part will become 2. So that's constructive interference. Okay, so that's very important. On the other hand, if delta is pi, or generally speaking, pi plus 2 pi n, because angles are defined modulo 2 pi, and so if that's the case, then this two sums of sines, well, you can clearly see that they become 0, because sine pi plus star 1 is negative sine star 1. So that's 0. And so that's completely destructive interference. So intensity will become 0. Okay, so that's another important finding here. So we got elementary conditions for constructive and destructive interference. Now there is one more thing to do. So how do we express this delta, which is k x1 x2 minus x1, in terms of slit separation d, slit separation d, and the angle of measurement theta. So let's do that. So the more detailed mathematics of this part is actually done in my later lecture note. So please refer to that if you want to learn more rigorous mathematics. But here we're going to make a reasonable argument. And so if L is much greater than d, it's obvious that this angle will be also about theta, and this other angle will be also about theta. Okay, and so this angle theta is rigorously defined as the angle between the horizontal line that passes in the middle from the slit aperture slit plate to the middle of the slit middle of the screen. But since L is much greater than d, if you make a horizontal line from the slit 2, and this is x2 vector, and that angle is also about theta, and this other angle for slit 1, the ray direction of the coming from slit 1, is also about theta. So now this is x2, this is x1. Hold on a second. Or maybe I reversed that. So this is x1 and this is x2. Oh my gosh. And what's the difference between the two? You can do a simple trigonometry here, approximately. So you can make a triangle here. You draw a perpendicular line to this x2 vector. And then you can see that this angle here plus that angle is 90 degrees by definition, because this is a horizontal line, that's a vertical line. But in this triangle, this angle plus that other angle here, that small angle there, is also 90 degrees, which means that this angle here is theta. And the difference between x1 and x2, that's about this guy here. So that difference is about d sine theta. Okay, d sine theta. Okay. So this is a good argument, but if you want more rigorous mathematical explanation, you can look at my lecture note. But anyway, so delta which is defined as k delta x, which is equal to k x2 minus x1. We just found out that this is actually k d sine theta. So then these conditions, and let me actually go further and say this is 2 pi lambda over d sine theta. Okay, so now we look at this, and then we look at those two conditions there for the constructive interference and destructive interference. We can rewrite constructive interference in terms of d and lambda and so on and so forth. So what is it? D sine theta equals n lambda. Why? Because 2 pi cancel out and lambda can go to the other side and multiply that integer n. And so in that view, if the path length difference is integer times lambda, then we have constructive interference. That's easy to understand. Destructive interference is when d sine theta becomes n plus 1/2 lambda. Again, here the n is an integer, so it could be 0, plus, minus 1, and so on and so forth. Okay. Okay, on the left slide, we learned pretty important facts about the double slit experiment, namely interference conditions, constructive interference condition and destructive interference condition. And we saw that the key quantity there was the phase shift, k, x2 minus x1, which is equal to kd sine theta. So now here we are a little bit more ambitious. So what we're going to try to do is to extract the full functional form for the intensity, not just the maximum or minimum positions, but we'd like to know the full function for the intensity function. Okay, so how do we do that? We need some trigonometric identity here. So let's see. The identity that we're going to use is this: sine A plus sine B equals 2 times sine A plus B divided by 2 and cosine A minus B divided by 2. And so you can learn to prove this, but here our purpose is just to use it. Okay, so if we use that, then what do we get? So here 2a over x1, and then if you add these two parameters, these two arguments here, and divide by 2, so what you get is star 1 plus delta over 2. And then what you get is cosine of this minus that divided by 2, so that's negative delta over 2. But since cosine is an even function, we can neglect the sine inside cosine, and so this is what we get. So let's make some observation here. So what do we have here? What we have here is that is basically a spherical wave. Why is that? Well, let's remember the basic setup here. We have a slit plate here, and at a distance we have a screen of where we measure intensity. And so basically there's x1 and x2, but those two are similar to the distance from the center of this slit plate to the screen. So this x1, x2, they're basically r, and we have this angle here, theta, right? That theta there. And so then this is y and this is L and stuff. So that's basically the setup here. What we need to notice, what we can notice here is delta 1 equals kx1 minus omega t and so on, but x1 is r, so it's kr minus omega t plus phi plus delta. That's that. So with that, you can see that this portion sine of star 1 plus delta over 2 over x1 is just another spherical wave formula. And so then what you can notice is that if you make the local approximation where the spherical wave becomes a plane wave, what is the amplitude of that plane wave? That plane wave has this amplitude A. So I'm going to put subscript PW for that plane wave approximation. So if you make that plane wave approximation, then you can easily write down the intensity formula for that, because why? We learned that intensity of a plane wave is basically proportional to A squared. So then the intensity, which is a function of y and t in principle, but actually it turns out it's independent of time, so that's just proportional to AP W squared, and that's proportional to, therefore, so I'm going to drop out 4A squared because that's just a constant, and so that's 1 over r squared and cosine square delta over 2. There's an additional factor here, and additional factor comes into play because why? The screen on which we measure the intensity is actually not orthogonal to the beam that comes to the screen. So what's the angle? Is there not 90 degrees? If you draw a perpendicular line to the beam like that, then you can figure out, well, this angle plus that angle is 90 degrees, and in this other triangle you can also say this angle plus that angle is 90 degrees, so that means this angle is theta. What that means is that intensity that you measure on the screen here, on the flat screen there, is actually reduced by a factor of cosine theta. So there's a cosine theta factor which slowly modulates the intensity as a function of theta. So that's it. So that's the final formula for the intensity in a Young's double-slit experiment where the screen of measurement is a vertical flat screen. We can do one more thing here, namely, sorry about this. One more thing here. One more thing that you can do is you can fix the proportionality constant here by just specifying the intensity at a convenient reference point. So let's say at theta equals 0. So that means delta equals 0, y is also 0. Let's say the intensity let's say that the intensity I0. So then what would be the I, y? So then you can write it as I0 L square over R square times cosine theta times cosine square delta over 2. So that's the final formula that we have. So let me actually highlight this. So this looks a little bit complicated, and so what it is that this R square is actually L square plus Y square. So we can make sure that this proportionality constant is actually entered correctly. Well, it is correct, because when y equals 0, this becomes L squared, so this fraction here becomes 1. And theta is 1, delta is 1, so all of those are 1. So that means I becomes I0. So that satisfies this reference condition that we just set up. The important point here is that of all these expressions, this expression here, cosine squared delta over 2, is of utmost importance. So that describes the fringe pattern of the double slit interference. These other things are just describing some geometrical factors like cosine theta and the fact that we have a spherical wave 1 over r squared type of thing. These are just slowly varying factors which are not that important. And so and in fact, most interference measurements occur for theta values close to 0 anyway. So these tend to be pretty much constant. So these factors are not that important, but here we work them out accurately anyway. Okay, so that's it. That's the end of lecture. Bye.